Hello. So, quick introduction about myself. I'm Ahmed Mostafa. Right now, I'm working as a tech lead for front end in Barclays Bank. And since maybe I should, yeah, okay. So I should keep it quite close to my mouth. Okay. So since the introduction of ChatGPT, everybody's talking about neural networks, and I grew sick of it. Everybody on the street right now is talking about neural networks, but most people who speak about it don't really understand what is neural network and why should we learn neural network, or what use cases our neural networks are good for. Most of the stuff that they want to use it is not really suitable for neural networks. So today I'm going to give a quick introduction about what is neural network and when to use it, when not to use it, and two other flavors of machine learning that can be very useful in some other situations. So as everybody knows, that neural network is mapped after the human brain. On the right here, we see an actual network, an actual neural network map for a brain. Oh, by the way, it's not only the human brain, it's any brain in the world. Any brain for any animal have the same neural capacity to it. However, our brain as humans is much larger, so it has much bigger layers, let's put it this way. That's why we can, like, we have this thinking capability more than an animal. So yeah, exactly just like the human brain or the animal brain, the computer scientists mapped it as a tree. It's also in the humans is some sort of a tree of neurons. We'll see that in the next slide. So on the right here, that's a biological cell of neuron. It has inputs, it has outputs, and it's connecting to another cell. In computers, we did the same. In computers, we did the same. We made a cell that holds some functions that we do some mathematics on. We have inputs, and then we have an output. This output is usually going to every other cell. Just like here, we have inputs into the cell. We do some mathematical operations here, and then we propagate the output to the other cells. So, since we have a brain, how do animals and humans work? How can you teach a dog to perform a new trick, or how do you teach a monkey to do something? As they say, monkey sees, monkey does. Monkey sees, monkey does, I think. I don't know. So anyway, so as with any new skill, you have to repeat it 1, 2, 3 million times until you learn it. And then it's not enough that you repeat it. I mean, it can be a skill that you take a piece of metal and put it in the electricity socket, but then you're going to get a shock, and that teaches you not to do it again. So here we have the idea of giving a prize. Let's put it this way: giving a prize and giving punishment. So we can see here, this is a very simple neural network that is in operation. We can see that the pathway between the neurons is getting heavier, and some other pathways are growing smaller in weight. And that goes with something that's called back propagation, which is basically like we are training the neural network, and when it arrives at a solution, we test this solution. If this solution is correct, we give the neural network some sort of, say, candy, or we give it a prize, so that the neural pathway that leads to the end is made heavier, so that it keeps taking it every time forward. And of course, yeah, like the exact opposite thing happens to the neurons that actually produced a bad result. We put some sort of punishment on it. We decrease its weight. This is a very simple idea. I'm not going into like pure math in this talk, because that's like a 5-hour talk on its own. But basically, you have something that's called, like, we have the inputs, we sum it up, we apply some functions to it. And the activation function in its own have like way so much details into it. I'm not going into that today, so that we can finish. But yeah, like the idea of neural network is monkey sees, monkey does, monkey does. So like the more you perform a skill and give some sort of prize to the neural network, the better it's gonna perform. So we saw, like in this slide, it was a very, very simple neural network. So how come ChatGPT can perform so much operations? Because ChatGPT is applying something that's called deep learning. So that's way too many layers in between. It's not only one layer, it's not only two nodes in this hidden layer. You add so many layers, you add so much training data that you train it over and over and over again until it can perform the same operation with some sort of accuracy every time. But it's the same operation, and that's the limitation of neural network. It cannot learn from new data. And training a neural network, oh yeah, this is the mathematical thing. I'm not going into that. You have the, I'm gonna share the presentation. If anybody wants to read more into that. So the limitation of neural network is that it depends on the training data. If there's any errors in the training data, the errors are there indefinitely. You can probably see it in ChatGPT if you ask it something and it gives you a wrong answer, and if you ask it again, is this the right answer? It would say, oh, sorry, no, this is the right answer. And it would repeat the same wrong answer again. It's because it does the same operation. It does not have the ability to learn. And if you want to teach it, even with backpropagation, it does not take only one time that you tell it it's the wrong answer. You have to repeat it more times until it learns that it's a wrong answer. There are also some problems that are not useful with neural networks at all. For example, like the parameters, like if you have some parameters in the financial markets, for example, each time the problem statement is different. Each time you need something else. It's not a good thing for neural network because it just repeats what it saw in the back, in the past. Yeah, the same problem statement is with routing of cars, routing of airplanes. The airlines are usually using more other techniques, we'll see it later on, in determining the routes of the airplanes, or the traveling salesman problem, as computer scientists know it for. So, what other methods are there? One of the most useful methods is genetic algorithms. We saw that neural networks is mapping the human brain. Genetic algorithms is mapping the evolution process of every living organism that came to Earth. So, how does genetic algorithms work? So basically, we have a problem statement. We have some inputs, we have some outputs, right? Like we have some entry data that the algorithm should give us some output based on. The output we call is the output we call as the solution space, or yeah, solution space. So the idea is we let's put it this way: we create a big amount of random answers to a specific solution, and then we test each of these solutions and see how is it fitting to the problem statement, how good is it solving it. And then we take the best solution and then we start crossing them over, which we'll see how we do the crossover, and we do some mutations in them, and we will get to that later on. And then we see, after we did all that, did the solution become better? Did we find a better solution within this population or not? So here we have a population. Each population is a group of chromosomes. Each one of these represents a solution. So like we take this chromosome right here, and it represents a solution. Let's take an example. In financial markets, for example, we have a lot of indicators, like we have a lot of patterns happening. And I want to know when should I sell and when should I buy. So what I would do is I say that I should sell if I see, for example, the trend at this part, if I see the other indicator in this part, if I see the price at this part, and so on and so forth. And then I do a simulation on that for the data, the historical data. If I produce a good result, then this is a high value solution. If I produce bad results, then this is a bad value solution. Okay. And then we do something that's called crossover, because high value solution is not the best solution. I'm always trying to look for the best solution. So I take two good solutions and I start switching the parameters between them. So for example, if I say this is sell, this is buy, I switch between them and say this is stays sell, this is stays buy, test it. Does it produce better solutions or not? If it produces better solutions, keep it in the population and remove the parents. If it produces bad solutions, remove it totally from remove it totally from the population, and that's not a solution after all. There's one more thing that's called a mutation. Assume I have a solution here. Okay, the mutation is the mistake that pretty much made evolution possible, because if everything is crossover, if everything is just breeding between two parents, we wouldn't have evolution. So the mutation is very important, and we're going to talk about it later on. We do the mutation and we test it. Is it producing a better solution or not? I'm not sure if you're following that, but we're going to get to it. This presentation is pretty dense. It's 3 years of research. So if you go out with 50% of it, that would be great for me. Here we have a genetic algorithm in action. This is just a simulation, but it's for actual robots. Like, so you can apply this algorithm on a dog, robotic dog, not a real dog, and it will be able to walk. So we have an input for this problem, which is gravity, which is the weight of the head, the weight of the tail, and our outputs are the muscle movements, the muscle of the leg, the muscle of the neck, so that you shake it, and the muscle of the tail, because it's using it for so that it doesn't fall. We see in the first generations, the robot wasn't able to walk very well, because it's not still like, doesn't know how to move its legs and how to move its neck so that it stays stable, it doesn't fall around. And with more generations and more generations, the algorithm could find the right muscle movements for the tail, the leg, and the neck, so that it stays stable. That's the idea of neural networks, of genetic algorithms, sorry. This is another example from NASA, Jet Propulsion Labs. And so, as I believe, this algorithm was trying to find the best fuel mixture for a rocket, so that it gets to like the highest altitudes. You can see that okay, once it repeats, you can see that it saw two best solutions, which is a difference from the neural network, because neural network always gives you the best solution that it had seen before. However, in here, we see that it gives you not only the best solution, it also can give you the second best solution and the third best solution based on the parameters you've entered and based on how much do you do crossover and mutation and how many generations have you created. I just wanted to repeat so that I can show you. Yeah, so here we have two local maxima. This is the best solution. This is the second best solution. And you can see that it's converging on the two best solutions on here and on here. So from what we've seen, why is genetic algorithms sometimes better than neural networks? Can anybody answer that? Okay, so genetic algorithms is better in determining the solutions in very complex search spaces. In here, like in the NASA image, we saw a two-dimensional space. Like say, I think it was a fuel mixture. So you have the fuel and you have the oxidizer, but you can add another layer on top of that. So it's a very complex search space. It's always changing. Not every rocket is the same as the other one. So you should use you should use genetic algorithms, because it's always searching for the best solution. The second good thing is that it's very computationally less expensive than neural networks. Neural networks, it takes years to design the right neural network. It takes years to train it. It takes millions of dollars because you need very large computers. However, in genetic algorithms, you can just slap it on top of your browser, slap it on top of your mobile. Even I've seen it slapped on top of Arduinos or Raspberry Pis, and it's performing greatly. It's not that computationally intensive. Yeah, me myself, I'm using it in financial markets to adjust my expert advisors, like basically algorithms that trade on my behalf. I don't have to sit in front of the computer and trade myself. It does it for me. Right now, I'm not doing much trading because I'm working in a bank, but I used to do that. Yeah, and you can use it like in game development. I've seen it used also in military, in smart ammunition, and basically the turrets that auto adjust to its target, so that it sees the sky and then it sees a target, it identifies this as a target, and then starts moving towards it and shooting it. So that was one flavor of machine learning. Another flavor of machine learning is particle swarm optimization. And by the way, in all machine learning, it's basically computer trying to mimic the living creatures or basically anything you see in nature in order to get to the intelligence. It's not really intelligence, it's just survival of the fittest, as genetic algorithm says. So particle swarm optimization is mimicking the behavior of birds searching for food. So this is an example also of particle swarm optimization. I'm not sure exactly what it is doing. However, this is a search space. And the search space means any viable solution for the problem. The solution may be very bad, and the solution may be very good, and we are trying to find the solution for a particular problem. Any problem that you can think of that can have a solution, mostly numbers, numerical solution. So we see here a group of birds trying to find the best place for food. This can be the same as in NASA image. Can be we are trying to find the best fuel oxidizers. It can be the same in financial marketing. We are trying to find the best parameters to make a sell or to make a buy for a stock exchange. However, instead of using evolution, in this case, we are using birds searching for food. So we will see the algorithm in a minute, but keep in mind that some of them found also the best solution, and some of them are lurking around another local minima or local maxima in this case, which is a good solution is just not the best in the whole search space. Yeah, so this is the algorithm. Basically, we make, say, a group of birds, which are possible solutions to a problem. These birds are initialized randomly, so each of them is just a random solution. And then we apply it on, like we test each of these solutions. Is this a good solution for my problem? Yeah, this is a great solution. Actually, this is the best solution we found everywhere in all the search space. So save it as the global best. What if it's not the best solution that I found in the whole space? Then it's my local best. So it's personal best versus global best. As a bird, I have a velocity. I have a direction that I'm flying at. I cannot just switch. No. So I start to take a turn towards the global best while keeping the personal best in mind. And why am I doing that? I'm doing that so that I can try to approach the best solution. However, maybe my local best is pretty good, so maybe I want to go back to it if the global best didn't come out as the best solution, let's put it this way. That's why we see some of them stuck here, some of them are stuck at a local minimum, and so on. Actually, there's a question. Do you know why, what is, like, in genetic algorithms, we saw that everything went to the best and second best solution. Do you know why in particle swarm optimization, they get stuck in solutions that are not so good? Yeah, go ahead, please. Something like that. But like the person who answers gets a prize from Atacama. Well, I would say that this one is stuck between a global best and a local best. Yeah, that's true. But this one is stuck away from any best. It can be. However, in genetic algorithms, there's something that is that exists in this flowchart that doesn't exist at all in particle swarm optimization. Yeah. That is part of the problem of slow conversion. Exactly, yeah. But I think you said it first, right? Yeah. So in here we have a mutation, and the mutation, the idea of mutation is that if you are stuck in a local minimum like that, I'm just gonna send you far away from the search space so that you can go to a better place. And that's why in here, if all the population, if the random numbers that we started with were all grouped here or were all far away from the global best, they would never converge there if it's particle swarm optimization. Each one would just go to their local minimum and nobody would ever find this. But however, in genetic algorithm, the mutation, the single mistake that made evolution and life possible is what sends all the search in different location in the search space so that it finds a better solution. So one of the example how to use PSO or particle swarm optimization is the design of aircraft wings. Because as we said, it's very complex thing. It requires that you calculate the drag, you calculate the lift, you calculate the width of the wing, you calculate the height, the thickness, the weight, the material strength, and so on and so forth. And of course, it's also very problem specific. If this is an aircraft from NASA, you need to fly it on very high altitudes. If it's a commercial aircraft, you need to fly it on low altitudes. If this is a jet fighter, you need it to be very agile, moving around. However, if it's like just a commercial airplane like we are all taking, you need to make it very stable as much as possible. So it's all very complex parameters. If you put all of this in one neural network, it will always produce the same result. However, in PSO, you can just adjust your parameters for entry, run it 5-10 minutes. My financial market robot, I used to run it for backtesting for 5 years, and it would take just above 2 hours. So I don't need that much money. I don't need that much computing capability to run a PSO or a genetic algorithm. By the way, PSO is way less computational intensive than genetic algorithms. But it's also like it applies in almost every case for genetic algorithms. They are almost, you can interchange them very commonly. So yeah. However, the bad thing about PSO is that it can fall into a local minimum. That's why you don't use it for something that will live with you for a very long time. Maybe usually you can put it into a self-driving car so that it can find the best route forward, right and left, right? It can also be used in the traveling salesman problem because it can also always find a very good solution, not always the best, but it can find always a very, very, very good solution. This is some of the usages for PSO. It's not my research. The research is here. It's on the University of, I don't remember. But here's the source. As I said, I'm going to share the application. You can just look it up, and you can see a lot also of healthcare applications. Yeah, so I know it's been very dense presentation. As I said, this is 3 years of research, and my information hasn't been updated for quite some time, but please shoot who have some questions. Actually, let me first ask one question. Maybe if you answer this very well, Atacama can give you the prize. How to use it as a front-end developer?
Any idea?
Behavior of users. Some behavior of users, some prediction, and something like this.
It's machine learning, so it's definitely a prediction, right?
Yeah.
Okay, more specific? Somebody knows something more specific?
As a follow-up for that, like preloading of the resources based on like expected behavior.
That is a very, very, very good answer, actually. Yeah, that is great, actually. So yeah, he gets a prize, please. Well, the most thing that this genetic algorithms and particle swarm optimization is being used right now is recommendation systems. And yes, like a lot of people are saying, no, recommendation system is coming from the backend. But no, actually, sometimes the backend is sending all the, say YouTube, for example, if I'm not sure how YouTube does it, but if I want to do it for YouTube like that, I would send all the subscription videos. And then based on the recent history or what I've seen the user interacting with the most, I would show the recommended videos in some order. Yes, exactly. Thank you very much. It can also be used on social media, like the recommended posts that you share, that you react with the most. Can use in like something like Amazon. The products, like if I go to Amazon one day and I buy a hammer, I don't want to buy a hammer every single day after that. However, like for example, Amazon sees that I'm buying 3 protein powders per 3 months, for example, and it can recommend that to me because it's seen much more reactions from me on that. And the preloading thing is amazing. That was great. Something else is seeing which buttons the user is clicking the most. So like if the user is going through 3 buttons until he reaches his desired place on the website, you can take these analytics and basically put the button back on the front page so that the user doesn't have to go through all these things. So yeah, as I said, anybody have any more questions? I asked the questions.
Maybe one from biology aspect of side. Does genetic algorithms use concept of introns? Because in real life, without introns, almost every mutation will be lethal. Introns. It's part of our DNA, which is not used for genetic expressions.
No, we don't use that. We are only interested in the DNA that actually produces a result. So each part of the DNA corresponds to an output, and this output can be calculated based on a fitness function that sees if this gene is the fittest to live or it's not fit to live, and then we can discard it in the next population. Yeah. So thank you very much. That was my time.
Thank you.